Do I hold it? It's orange, but it's not. Oh, there we go. No, it's not doing anything. Should I hit play? Oh, okay, and then hit record. Okay. Now the numbers are doing something. You forgot to tell me about the play part. Thank you, honey. I did do that. Say it again? Your final is not cumulative. No. I used to try to squeeze one in, but I need to cover all the topic material. So your last test is basically your last exam. Okay? The whole course is cumulative, pretty much. Because if you don't get the beginning stuff, you're not going to get the... Yeah, exactly. All right, and speaking of cumulative, the dirty word for today's topic is chemistry. Who's afraid of chemistry? That's right. Don't be afraid of chemistry. Chemistry is not a scary thing, okay? That word, it's like math. You say math and everybody goes, ah! No. You must be one with chemistry because you are one giant chemical reaction. And in order to understand your physiology, you gotta kind of be in the chemistry train of thought. And we're going to go very basic chemistry. So I'm not going to make you count orbitals and planes and all of that stuff. And I'm not going to make you get your little models out like the organic guys do. But we need to understand basic chemistry and how chemistry works. So that's what this chapter is all about. The universe as we know it is made up of stuff or matter. That's the stuff you're made up of. That's the stuff your atmosphere is made up of. And those are made up of very tiny building blocks called atoms or elements. So how many atoms or elements do we have in our environment? Do you know? Shh, don't tell anybody. I ripped it out of the back of the book. But you have one of these, don't you? What is that thing called? That's the periodic table. When you go to chemistry class, you're going to have to know all of these things, memorize the symbol and all of that good stuff. We're not going to make you do that. 4 major ones is the basic bulk of your matter. Anybody take a stab or guess at what those 4 major atoms or elements are? Remember, CHON. Carbon, hydrogen, oxygen, nitrogen. Is that it? No, there's a whole bunch more. But the bulk of your matter, your human body matter, is those 4 guys. And we put them together in different ways to create different molecules and different chemical reactions in the body. So there's about 92-ish on this chart. And some of those guys we actually created in the laboratory. Yeah, those guys down near the bottom. Okay? So that's your periodic table of elements. And when I take these guys, these single guys, and put them in different combinations, they form different types of this stuff that you live on this planet and are made of. So there's different states of matter, different forms in which this matter exists. That's what that means. So what are the states of matter that we're going to discuss in this class? Solid, liquid, gas. That's it. There's more. We're not going to get there. Okay? That's chemistry class. That's physics class. We don't need to know that stuff. Eventually you might need to know that stuff, but I'm not going to make you know that stuff. So solid and liquid and gas are some of the different states of matter that we'll find these atoms or elements. When they come together, what do we call them? Molecules are in on our planet. We also have a very important something else that we have to talk about with regards to chemistry, and that's energy. Now, energy. That's the ability to do what? Work. You need energy to do work. You need energy to get up in the morning and go to work. Yes? What's your energy source? Some of us go right to Dunkin' Donuts and get the big one. Yes? Need a little that's an extra little speed up chemical reaction energy that we might require for our work. What else, though? Can we live on coffee alone? Yeah, we need food, we need nutrients, water, big, huge, important that we need, because that's where all of our chemical reactions are going to kind of take place, in that big soup or water. So we need energy to drive the reactions that we're going to talk about in this class. And collectively, they're called reactions of metabolism. So when I say metabolism, what else could I say instead of metabolism? Yeah, chemical reactions. Now, some of them have different categories, like the chemical reaction that helps our bodies make the energy we use to drive our chemical reactions. That reaction is called cellular respiration. But that is a reaction of what? Metabolism. Yes? It's a chemical reaction. See, they're all kind of interchangeable terms. So energy, the energy we use to drive our reactions of metabolism, come in several different forms. And they talk about that in your textbook. Chemical energy. Where do we get chemical energy from? Or chemical reactions. Anybody ever make like a volcano in elementary school? Did you do that? Okay, if you didn't do it, you missed out. We'll tell you how. How? Vinegar, baking soda. Two things that kind of hang in doing nothing, but when I put them together, what happens? Volcano. That's chemical energy. The energy that's given off. And if you put those things in a beaker, what do you think is going to happen to the beaker? Besides all the foamy stuff that forms, and that's a gas given off by the chemical reaction. Feel it. It's going to get warm. So that's energy given off by chemistry. Okay? And that's what chemical energy is. Electricity. Yeah, movement of charged particles. When we talk about these guys that I ripped out from the back of the book, all of these guys are neutral. And we're going to describe what that means in a minute. But when these guys lose some of their subatomic charged particles, they then have a charge. And that's what a charged particle is. The movement of it from one place to another actually gives off energy that I can use to do work. You plug stuff into an electrical outlet. And what happens? How come? Charged particles are moving from one place to another, giving off energy, and you're using that energy to drive things like the washing machine and the refrigerator and so forth. Mechanical energy. Do this. Put your hands together. Go like this. What's happening? It's getting hot! Yes? Heat, energy, movement, giving off energy. We can use that energy to drive reactions of metabolism as well. Okay, and if you put, you've probably seen some commercials. There's a commercial where this guy's on a bicycle and he's riding in the back room and everybody's using their electrical devices, and he stops and all of their electrical devices shut off. You ever seen that? No? Well, imagine that. And that's mechanical energy. And then we have a big one, and without it, we wouldn't be here on this planet, that provides energy for us to survive on our planet. Who's that? The sun. And what type of energy does the sun give us? Radiant energy. And that energy drives reactions of metabolism. That energy is the reason why plants can do what? Photosynthesis, which is what? They make their own food. And then they take that food and they break it down in another reaction of metabolism to make energy. What do we do with plants? We steal their energy. Because we can't do what? We steal their energy. Wrong. We steal their carbohydrates, which we use to do what? Break down and make our energy. Okay? Plants can do both. So we have to eat stuff in order to throw them in our reactions of metabolism to create our molecules and to make energy. So yes? What is the composition of matter? I don't know. It's freaking. She's freaking out. No, but for some reason my thing won't move. There we go. Okay, so composition of matter, atoms, and elements. If you're in chemistry class right now, you're going, oh, she's forgetting so much. Yes, I am, because we don't need that for A&P, okay? So, elements, what are they? Those guys. They're the smallest what? Can we break down these guys any further and have them be elements anymore? No. So there's the smallest, simplest units that we're going to talk about when we talk about our chemistry as humans. At present, ooh, the number went up. 112 elements are known. And again, that number might change depending on the textbook, how old the textbook is or how new the textbook is. That number's changing all the time. We can artificially create elements, and they have to be stable for a certain amount of time, which might not be that long, in order to make the list. So that's why the numbers are constantly changing. But naturally occurring elements, the guys on this list, 92. So the rest are made artificially with particle accelerator devices, and most of us don't carry those things around with us. So those are the others that make up the list. The four main ones, carbon, hydrogen, oxygen, nitrogen. Again, that's the bulk of your matter. Periodic table, way in the back of your book, lists all of the 92 that we mentioned before. And each of these guys are made up of several different little building blocks. Each element on the periodic table is who they are because of what? Hydrogen is hydrogen, and helium is helium, and lithium is lithium because number of protons! And protons hang out kind of in the center of atoms or elements, and they are one of what atoms and elements are made of. We call them subatomic particles. So helium has one proton. Yes? How do I know that? Because it's number one on the periodic table, exactly. There's a number above each of the atomic symbols on your periodic table. And guess what that number is? That's the number of protons in each of these guys. So I'm wicked smart. I can just go and say calcium has 20 protons. Right off the top of my head. If you look at your, I know I'm wicked smart. A8 is where your periodic table is in the back of your book. But if you go and look at that periodic table, you'll see that calcium has the number 20 above it. And that tells me the number of protons. Again, what do we call that number? That's the atomic number. And that is the number of protons. So nobody on this list, and I dare you to find one, nobody on this list has the same number of protons. Because that makes me who I am. The other subatomic particle we might find hanging out, right in that central region of each of the atoms and elements, is something called the neutron. By the way, a proton has a positive charge. What does a neutron have? No negative. Neutrons are neutral. I know that's bad because you say protons positive, neutrons neutral. And we find those in the central regions of the atoms or elements as well. These two guys are the heaviest of the subatomic particles. And the combination of the two gives the atom or element that I am talking about its mass. So the number on the bottom of the atomic symbol on the periodic table is a bigger number, isn't it? Anybody looking at your periodic table? I don't have one on the overhead. I should probably put one on my overhead. That would be a good idea. That's a bigger number. That's called your atomic what? Mass. No atomic weight. In the old days, we used to call it atomic weight. No, we don't call it that anymore. Weight. It should say atomic mass. Does it say weight? Shame on you, Elaine Marieb. It should say mass. That's a more proper term to use. When I weigh myself, guess what else plays a role in my weight? Yeah, the whole atmosphere and gravitational pull. Like if I want to lose a quick 10 pounds, guess where I can go? To the moon. Will my mass be different? No. But my weight will. I'll be lighter. Could also climb Mount Everest. Yeah, I'd rather just hang with the weight I have, but you get my point? So the more proper term is atomic mass. And the mass is made up of the number of subatomic particles that you possess. The ones that are meaty. There is another subatomic particle. It's much, much smaller, and it's constantly on the move. And those are called electrons. And they tend to orbit the outside. They're moving very, very quickly and orbit the outside of what we call the nucleus of an atom or an element. The nucleus contains protons and neutrons, and it has most of the mass. Each proton and each neutron have one atomic mass unit of massness. I don't want to say weight, but you getting the point? That number, the atomic mass at the bottom of the elements, is a combination of what? Protons, neutrons, and electrons. But electrons don't have a one atomic mass unit of mass. So you see the point whatever beside it, that's the electrons. So if we look at the whole numbers then, we are talking about the number of protons and neutrons that these guys on this page have. Yes? We good so far? Yes. Good. So, we know what an atomic number is. We know what the atomic mass is. We know that atoms are made up of subatomic particles, protons, neutrons, and electrons. Yes, sir?
Which ones are the ones that have the same amount? So they're subatomic protons, neutrons.
Okay, now here's how the tricky way I'm going to have you remember this. Everybody on this paper is neutral. And in order for me to have a neutral charge, what do I have to have with respect to positive and negative charges? Equal amounts. Yes? So, back to the subatomic particles. Protons, positive. Neutrons, neutral. We're not going to talk about them. And electrons, negative. So on this chart, and only on this chart, and just here on the chart, everybody is what? Neutral. So the atomic number also equals what? The number of electrons. It actually is the number of protons, but just these guys here on the chart are all what? So that number also equals the number of electrons as well. Not in nature, though, because I'm constantly losing and gaining electrons through chemistry. So if I took a molecular camera right now and took a snapshot of all the molecules in your air, it would be very confusing. But I wouldn't find just hydrogen and oxygen and nitrogen and water vapor. I'd find them in their neutral form, but I'd find a lot of them as charged particles as well. Okay? But again, just on this chart, am I making my point? Only here they're neutral. All right, so we know what an atomic mass is. Table 2.1 on page 26 shows us some of the more common elements composing the human body. And again, we see the major ones, 96.1% of your composition are carbon, hydrogen, oxygen, and nitrogen. Even though they're in lesser amounts, it doesn't mean they're less important in chemistry, but we see things like calcium and phosphorus, potassium, sulfur, sodium, chlorine, magnesium, iodine, and iron on that list as well, as long as a lengthy list of trace elements that we find in the body as well. All of them are important for normal function. Now, remember I told you about those electrons? They're constantly flying around the outside of the nucleus of their element or atom that they belong to. And these guys, the electrons, are going to determine my chemical reactivity in the world. Back to the chart. Everybody's lined up really nice and neat. Well, how come? They don't want to who?
Because the ones at the very end to the Calais, I guess, are the ones that are settled and are happy with the payoff, but the other ones won't.
Ah, okay. You're on the right track. If you look at the purple ones in particular on your chart, the purple ones have Roman numerals above them. And the Roman numerals tell us something about them. It tells us something about the electrons they have in the very outer orbital of that atom or element. Now, I don't want to confuse you because that's the chemistry teacher's job. But these electrons can only move around in a certain three-dimensional space. If they try to cram too close to each other, they'll smash into each other. And you know what happens when atoms smash into each other? Big, huge, gigantic atomic bomb explosions. So we don't want them banging into each other, right? So when they rotate around their given element or atom, they're going to keep their space. There is a first orbital in which I can only fit 2 electrons. If I try to cram any more in, what's going to happen? Boom! Yes? So 2. Only 2 can fit in the first orbital. When we start getting more electrons, and you can see that tons of these elements have more than 2 electrons for sure, right? We have to make sure they move around orderly around the nucleus of that atom or element. So we have to move them out just a little bit further so they can have their space. The next orbital, the second orbital, because of the three-dimensional space it inhabits, can have a total of 8 electrons. And every one after that, guess what they can have? 8. It's not total in an energy level. Energy level, orbital, little bit different term. But what I want you to remember for anatomy class is that the outer electrons in all of these guys will be happy if they have more than one energy level with 8 electrons flowing around the outside. And that's the Octet Rule they mentioned in your book. There's only 2 guys on this list that don't follow that rule. Its outer electrons are what? 2. Because it only has 1 energy level. Do you know who the 2 guys are on this? Hydrogen, H, and all the way over on the other side, helium. Hydrogen has how many electrons? 1. How'd you know that, smarty pants? It's the same as the atomic number, right? How many electrons does helium have? 2. You knew that because of? Correct. When we have a full energy level, we are happy. If our energy level is not full, we are chemically reactive, out there trying to fulfill that full outer energy level. So hydrogen is very chemically reactive because it's either going to give up one of its electrons, the one it has, or it's going to try to do what? Gain another electron to fill up its outer shell. That outer shell, the outer electrons, has a name. What do we call it? Yep, valence electrons, those outer electrons. And there's 2 numbers to remember for anatomy class. 2 and 8. So everybody on this chart besides hydrogen and helium want to have 8 in that outer shell. So that's chemical reactivity. So we can identify the elements. We know what the atomic number and the mass number and the atomic weight or atomic mass and the difference between what that means is. What's a radioisotope? Ever hear of radioactivity? Yeah, things are kind of shooting off of those guys all the time. Subatomic particles. So, again, these are all the neutral guys, these are all the base, but that's not how they're going to exist in nature. So sometimes things lose neutrons. And decaying elements or atoms are said to be radioactive. Now, radioactivity is also around you all the time. Most of it is harmless, but some of it can be harmful if the energy that leaves when that particle leaves is a very strong amount of energy. Alpha versus gamma rays is how we describe the energy that leaves when a particle leaves. So what's the best one? The radioactivity that you wouldn't mind being bombarded with at all times. Alpha. That's okay. It's just going to kind of bounce off your skin and we're good. Gamma rays, on the other hand, bad. Because they're not just going to bounce off your skin. They're going to go through your skin and damage your cells and destroy your organs. See the difference? You can't see this energy, can you? No. So I wanted to mention something about radioisotopes. We use radioisotopes in medicine all the time. The weaker ones. The ones that have what we call a very short half-life. Because every time a particle or group of particles decays, typically half of it leave and they leave half behind. That's called the element's half-life. So we tend to use ones with a very short half-life that give off a very weak energy. And we can actually see this energy that's being given off by these things on who uses most radioisotopes? What department in the hospital? the radiology department. So we can actually picture these particles decaying. We use substances like radioactive glucose to try and find tumors, for example. Why do you think they would use radioactive glucose to find a tumor? If I tag the glucose so that I can see it when in the imaging department, because that's another name of radiology, who takes up more glucose, normal cells or abnormal cells? Abnormal cells. So I can actually visualize where a group of abnormal cells might be by using some of these radioisotopes to help me do that in the imaging department. So they mention it in your textbook as well. All right, so how do these guys combine? How do they come together? Why do they come together? What is the goal of every atom and element? To have 8 or 2, that full outer orbital. Now, how do I know how many outer electrons these guys have? Let's go back to the purple guys again. How many outer electrons does hydrogen have? 1. It's only got 1 electron, so that's a good guess. But how many outer electrons does cesium have? That's CS. Big C, little s. I'll give you a hint. It's on the right side of the page. That's right side of the page. Well, when you're looking at the book, it's on the right side of the page. Big C, little s. Let's get an easy one. K, potassium. It's in the same place cesium is. K, how many outer electrons does potassium have? She's like, how in God's name am I supposed to know? Well, let's draw it out. These are representative of how things look in the chemistry world, yes? How many electrons I have, how many neutrons I have, all that good stuff, right? All right. So if I look on the periodic table, let's look at these guys. Hydrogen has 1 electron, 1 proton. That's how we draw it. Radioisotopes of hydrogen that maybe gain neutrons or maybe even gain 2 neutrons are what we see here, deuterium and tritium. But we draw these guys out based on how many electrons they have in this model. And this is going to help us with the reactivity of atoms or elements. So, my question to you was potassium. How many outer electrons does potassium have? Well, yeah. How'd you know that, Smarty? Well, yeah, let's draw it out. So potassium is here, yes? And how many protons does it have? Look at the chart. 19. So we're going to pretend there's 19 little protons in there. And how many, here's a trick question, how many neutrons does it have? You think it has 19? The atomic mass is a combination of protons and neutrons. And the atomic mass of potassium is what? 39. Let's look at the whole numbers. What is 19 from 39? Yep. So potassium has 20 what? Neutrons. And we won't write those because that's a pain in the neck. So, and how many electrons does potassium have? It's got 19. Remember we said these neutral guys? So let's draw them out. The first orbital has how many? 2. Pardon my drawing. The next one will have what? 3, 4, 5, 6, 7, 8, 9, 10. Oops, we have 9 left. Where are we going to put them? Let's put them in another here. There's 8 here. I'm not going to draw them out. And then there's 1 more. I just drew the number 8 because I didn't feel like making the dots.
No, on the line, there were 9 left. You said there were 9 left.
Yeah, there was 9 left after I drew the second orbit. See that? How else could I tell there was 1? Yeah, everybody in this group, 1A, everybody here, so cesium, has 1 outer electron, 1 valence electron. How about in group 2? Take a guess. You got it. Lithium has 2, so is lithium up here? No, we can draw it out quick over here. So lithium, let's go through it. How many protons does it have? It's got 3 protons. How many neutrons? No. Yes, 3. I'm sorry, I thought that said 9. My glasses. So it's got 3 protons, 3 neutrons. How many electrons? 3. Draw them out. First orbital has what? 2. The last one has 1. So what does lithium want to do? Gain 7 electrons. That would be hard. Yeah. So we're going to talk about reactivity in a minute, but we want to strive for a full outer shell. If lithium pitched that little electron, which would take less energy to do, and gave it off to someone else, it would have a full outer shell. It would be happy. Yes? Go all the way over to the right-hand side of your page. Group 8. Guess how many outer electrons that guy has? 8. Is that going to be very reactive with anybody? No. I'm happy. Leave me alone. So helium, neon, argon, all of those guys in group 8, we call them the noble gases because they're not very reactive. They aren't reactive with anybody because they're stable. And they all happen to be in gas form as far as matter goes. Yep. Yep. Well, fluorine is in those, but neon lights, neon gas. Okay? So those aren't reactive, but everybody in between wants to strive to be full. The guys in group 7, how many valence electrons do they have? 7. What do you think they want to be happy? 1. Sodium, how many electrons, valence? It's all the way over on the left. 1. How many valence electrons in chlorine? Go to the right. 7. Sodium chloride, do you know what that is? Salt. Easy to make. All over the place. Why do you think? Because they're very reactive with each other. So all the guys in group 1 and all the guys in group 7 can potentially react very easily and make each other extremely happy. You see where I'm going with the whole chemistry thing? So the valence electrons of any given atom or element or molecule are going to determine their reactivity in the chemistry world. The guys in group 2 want to do what? Either gain 6 electrons, which is really hard to do, or get rid of 2 electrons. Now some of these guys, the way they react is going to depend on how much energy is available and what they have to do, either gain or lose. We also have reactions that'll share electrons when we start getting to the areas like C. What's C? It's kind of in the middle right-hand side of the page. Carbon. How many valence electrons does carbon have? 4. How many electrons does carbon want to be happy? 4. Carbon meets carbon, everybody's happy. When we talk about chemistry, there's 2 major divisions of chemistry. There's what we call inorganic chemistry and organic chemistry. You know what the difference is?
Organics hard.
Organics who?
Hard.
No.
What has carbon?
Yeah, exactly. Organic molecules have carbon in them. Inorganic molecules don't. Yes? That's it. Now, because the whole carbon sharing electron thing happens, carbon tends to form very huge chains of carbon and very large molecules. So when you have to take organic chemistry, you're going to talk about very large molecules, and many of those molecules we're going to talk about in this course.
That's why it's harder.
It's harder. Oh, okay, now I get the hard part. I thought you were talking like hard.
No.
All right, so things mix together or come together in chemical reactions in different ways. And they talk about differences between compounds, molecules, ions, and all of that good stuff. By the way, this should all be repeat information for you. That's why I'm kind of going fast. You should know all this stuff already from before you came here. Oh, well, we're going to learn it. Yes? So, when I bring two or more atoms together, I now don't just have an atom anymore. I'm not single, I'm married. I've chemically reacted, and I can form molecules. If I took that snapshot of your environment again, I would notice that most of the oxygen that's hanging around in this room isn't just O by itself. There's two of them that hang together, and it's O2. Same with hydrogen, H2. So we like to hang together so we can form stable structures. Different kinds of atoms that bind form things like compounds. And compounds, molecules, combinations, mixtures, solutions come in many different forms. So solutions tend to be more evenly distributed mixtures of things. And notice most of these things are in what? In containers. Because why? Yeah, liquid. Liquid, what's the liquid? Yeah, water. Water, 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 water. Because all of these guys are going to mix together more evenly in this wonderful universal solvent we call water. So solutions, particles evenly distributed in some kind of solute. And there's two things you need to know, what the difference between a solute and a solvent. And I mixed that up, so cross that out in your notes. Water's a universal what? Solvent. I said the wrong word, I just realized it. I apologize. Erase that. And if I were to take some salt, for example, back to the salt again, and throw it in my water, what would the salt be? The salt would be a solute. So the things I'm dissolving in something is a solute, and the something I'm dissolving it in is a solvent. So many of the solutions that we talk about are mainly water-based when we talk about many living systems. Now, sometimes solute particles are larger, and they may not evenly distribute themselves into my solvents. They might even be so heavy they settle out. Huh? Yeah, and that's the next category, colloids, that they talk about. And sometimes they're so large that they don't really evenly distribute at all. They might scatter light rays, and we use light rays a lot to try and determine the concentration of things floating around in our fluids. And blood is an example of that. That we call a suspension. I used to be able to use an example. There used to, years ago, be a nasty drink they had on the market, and you looked at it in the drink case, and there were all these little balls floating around in the drink. Did you ever? I don't remember the name. Orbits. That's it. That it was called Orbits. It was a beverage. And it was nasty because in order to be that suspension, it's got to be a little thicker to suspend those little things. Did you drink it in 4th grade? Yep. That was a good example of a suspension. I don't know. I never, it just kind of freaked me out. Was it like, it's like runny Jell-O almost, right? Yeah. And the kids used to pick them out. All right. So, there's differences in the consistency of solutions depending on how heavy or large the molecules are that we are trying to dissolve in solvents. If I want to find out how many molecules I have in something, we actually have a way to do that. And I'm going to really quick give you an example or give you an explanation of something called Avogadro's number. It's not avocado's number, it's Avogadro's number. And if I look at, and the explanation for this is on page 30 in your textbook. If I want to find out or determine the number of atoms of something I have in any given solution, I can use Avogadro's number to help me. Something called a mole, and you chemistry people have heard that before, right? A mole of something is how many molecules of something or atoms of something. If I have 1 mole of carbon, how much carbon do I have? It's a huge number. Yeah, and that's Avogadro's number, 6.02 times 10 to the 23rd molecules. So if I have a mole of a substance, I have 6.02 times 10 to the 23rd molecules of the substance. That's a lot, right? Yes. 1 mole equals that, always. Now, when I'm making up a solution and I have to be exact as to the concentration of whatever it is I'm putting in my water is going to be, that's when I use this number. So if I want a 1 molar solution of sodium, for example, and I want to put it in 1 liter of water, how much sodium do you think I need to put in that 1 liter of water to make sure that I have 6.02 times 10 to the 23rd molecules of sodium? Anybody? I need a mole of it, but what's a mole of sodium? How am I going to get that and put it on the balance and get a mole of sodium? Get the atomic mass. And that's how many grams of whatever's on this table is going to give me 1 mole, or 6.02 times 10 to the 23rd. Isn't that cool? So if I ask you to make up a 1 molar solution of sodium, you're going to weigh out 22.99 grams of sodium, and you're going to put it in what? 1 liter of water. And you'll know that you have 6.02 times 10 to the 23rd sodium molecules, or sodium ions, let's call it. Yes? That's what that means. I wanted to touch on that. I just didn't want to ignore it, because maybe someday you'll take chemistry and at least know what a mole is. Yeah. Yeah. If I'm talking about it, it's important. Okay? So, they talk about the difference between mixtures and compounds. I'm not going to get crazy about that. Chemical bonds, the role of electrons in chemical bonding. So electrons is going to determine whether or not I'm attracted to somebody else. That's what a chemical bond is, an attraction of one element or atom to another. And that outer electron shell is going to determine my reactivity with others. So chemicals that are not attracted to others are ones that have a full what? Yeah, the full outer shell. So anybody from group 8, and helium and neon are both there, are not going to be reactive with other atoms or elements. What do we call these guys? Well, we call them the noble gases, but we also call them inert. Chemically inert elements live in group 8. They're not very reactive because they're already what? They're happy. They're full. So chemically reactive elements are who? Everyone else. Striving to do what? Fill that outer electron shell. So remember, if I'm on the low end, like I have 1 valence electron or 2 valence electrons, I can easily give them up to be stable without too much energy. When I start talking about guys like sodium with 1, not a big problem. But if I start looking at the guys like oxygen with 6, what does oxygen want to do? He wants to gain 2 electrons. It would be really difficult for oxygen to lose 6 electrons. So do you see the difference in whether I want to lose or gain? It has a lot to do with the number of valence electrons. Carbon's smack dab in the middle. So carbon tends to want to share or gain electrons. The next part of the textbook talks about some of these different types of chemical bonds or attractions between atoms and elements. Now the guys that want to give up or gain electrons form a type of bond called an ionic bond. Remember, electrons have a charge. Yes? What's that charge? Negative, right? So if I lose an electron, I no longer have an equal number of positive and negative charges, right? If I lose an electron, I have 1 less negative charge, and I become a positive charged particle. Let's not call him charged particle. Let's call him an ion. Okay? If I gain 2 negative charges or gain 1 negative charge, now I have 1 more negative charge than a positive charge. I am now charged. I am a negatively charged ion. What kind of bond is this? It's called an ionic bond. And here's my buddy sodium and chlorine up there again. Bonding and reacting in the chemical world can give an atom or element a very different form of matter. It can change it a lot. I'll give an example. Anybody ever see pure sodium? It's a metal. If I expose it to water, it blows up. Yes? Pure sodium. If I store it in the lab, what do I have to store it in? Anybody know? Oil. So no water gets near it. So it doesn't blow up. Chlorine. Pure chlorine. Guess what it is? It's a poisonous gas and it will kill you. When the two react to form sodium chloride, you sprinkle it all over your eggs in the morning. Because it's changed now, right? It's got very different properties after the chemical reaction takes place. And again, sodium, and you can see these guys on the table, has 1 valence electron. It tends to give it up in an ionic bond. And chlorine in group 7 wants to do what? Gain. See why they're so attracted to each other? The only way that sodium and chlorine are going to react with each other is if they are close enough to each other to react. So even though sodium and chlorine are very reactive with each other, one of the things we have to remember in chemistry is we have to bring them close enough to react. We have to kind of be a matchmaker. Because if I had a chlorine all the way up at that side of the room and a sodium all the way over here in this side of the room, is there chemistry going on? Not going to happen. All molecules are in motion. Did you know that? And no matter what state of matter they are, molecules are in motion. Unless they are at, anybody know? 0 degrees, absolute 0 degrees Kelvin. Can we achieve that? No. Not as far as I know anyway. Okay? So molecules, all molecules are in motion. Is that in motion? Yep. Solids, liquids, gas. Who's the fastest? Gases. Gases move the fastest. Who's next in line? Liquids. And then the slowest ones of all are the solids. So, we have to get them close enough together to react in order for them to react. And if we fall into those outer edges of the periodic table, we're probably going to tend to form ionic bonds, trading electrons, either gaining them or losing them. When this happens, sodium now has what charge? It's got a positive charge. It's a positive ion. It's a cation. When this happens, what's chlorine? It's a negative ion. It's negatively charged. It's an anion. And the movement of charged particles from one place to another defines what? Electricity. So these guys are really important in our bodies for the movement of them from one place to another for electricity. Can you think of a system off the top of your head? Aha! The nervous system. So when we start talking about nerve impulses, we're going to start talking about the movement of these guys across plasma membranes. Yes? See why you have to know this stuff? The carbon guys, the guys with the bigger, that kind of middle number of valence electrons, they don't give up or gain. They tend to do what? They tend to share. That's more efficient, less energy. I can form some really nice molecules, some really nice bonds, and be very stable. So carbon, with its 4 valence electrons, tends to hang out with something that can satisfy it, give it its 8, but doesn't throw away those 4. It shares those 4 with whatever it's binding with. This molecule is called methane. CH4. So what do I have? A carbon with 4 valence electrons and 4 what? Hydrogens with what? 1 valence electron. What does hydrogen want to be happy? It wants 2. So if it shares a pair with carbon, am I happy? Yes, then I'm going to invite 3 more of my friends to form methane. Very common gas in our environment. Yes? You see why? Easy made. So CH4 is methane. And this type of bonding is called a covalent bond. Again, oxygen atoms, how many valence electrons in oxygen? Look on my chart, or look up on that. It's in group what? 6. What do I need to be happy? 2 more. I don't want to get rid of 6. And sometimes it would be hard for me to gain 2. Why don't I form molecules where I can share? Maybe with a neighbor, another oxygen. So most of the oxygen we see in the environment is actually in this form, the resulting molecule of a covalent sharing bond, and that is oxygen molecules, O2. So you see the difference between covalent and ionic. And see the little lines? I'm telling you, this is what element is this? It's nitrogen. And how many pairs of electrons does it share? It's sharing 3 with its neighbor, We use 3 lines to tell us that. How many pairs of electrons is this guy sharing? 2. How many pairs? 1. So those lines in the structural formulas of these guys tell us how many pairs of electrons we're sharing. All right, now we're going to blow your mind, but not until Thursday. So make sure you read the rest of this chapter, because probably 90% of you didn't read the rest of the chapter. We're going to pick up with polar and nonpolar molecules on Thursday, and we will finish chapter 2 on Thursday. Yes? Another quiz, yeah. See how that goes? Don't